Okay, so welcome back. As I said, your homework will be posted sometime later tonight. When I say later tonight, and this is true not just for this homework, but also in general when I say something pertaining to when I'm going to post something, you got to give me like, I don't know, like a good, it's like plus or minus a day, because, my sleep schedule's funny, so what is like tonight for me is, not necessarily tonight for you all because I sleep at weird times. So, sometimes I'll post something. When I say tonight, maybe it'll be like, I don't know, like 4 a.m. or something. So anyway, it will be posted and you'll have plenty of time to do it. It's not like I'm going to take away the time that you have to do it because I, post it whenever I post it. So you don't have to worry about that. But when I post it, you don't have to pay attention to anything else. I'm not going to just say it in lecture. Whenever I post it, I will always announce, that I'm posting it. And like I said, I will try to remember to take pictures of the homework problems so that you will have those as reference. But it's going to be, this homework at least is going to be directly from the textbook. So it will be some problem set containing problems from most of the sections in chapter 11. Okay, so anyway. Last time we had defined the cross product and at least done at least one. I think we did 2 examples of computing with the cross product, and I ended with this fact that the most important use of the cross product by far in this course is as a way of generating a vector that is orthogonal to 2 given vectors. And I explained how kind of the idea here is the following: if A and B are both in this plane, that is this paper that I'm writing on, then A cross B, and maybe these are a little small, so let's make bigger vectors here. So let's say that I have a vector A and another vector B. Okay, and both of those vectors lie in this plane that is the paper here. Where is A cross B? So the way of determining the direction of A cross B is the following. I take my right hand and I let my fingers of my right hand curl towards from A to B if I'm computing A cross B. So if the thing I want to visualize, why did I do that? So if the thing I want to visualize is A cross B, then I take right hand, I take fingers of right hand, and I let my fingers curl from A towards B. Okay, of course it matters. We saw last time that A cross B is not the same as B cross A. So the order matters here. So whether my fingers are going from A to B or from B to A definitely matters. And so A cross B, I would take fingers, let them curl from A to B, and then I would pay attention to the direction that my thumb points. My thumb is going to point in the direction of A cross B, and A cross B is going to be some vector in this direction sticking directly out of the paper. Of course, because of the angle of the camera here, maybe this looks weird, but this is sticking directly out. Right, there we go. Sticking directly out of the paper here. Okay. All right. Now, of course, you can automatically see what happens if I do B cross A. So if I do B cross A, I take my right hand, I do the same thing. I let my fingers of my right hand curl. I don't have enough room here, but I let my fingers curl from B towards A, and this points directly into the table here, or into the paper. So it is exactly the opposite direction. So B cross A, it points in exactly the opposite direction. In fact, we already know that A cross B and B cross A are related by a flip of minus sign, right? There's minus sign involved. So anyway, okay, so that is visually what's going on. So let's actually write out this fact. There's a very important fact here. So maybe first, before I list that important fact, I'll say some general facts about the cross product. So let's just list a couple. We have, first of all, that A cross B and B cross A are related by this fact that A cross B is minus B cross A, or similarly B cross A is minus A cross B. Okay. All right, next. If I scalar multiply vector A and then I cross that vector with B, how is this related to, say, doing the same thing except in the B slot? All right. Well, these are equal. In fact, they're both equal to just scalar multiplying A cross B itself. Okay, and you can check that if you like. Just from the definition of the cross product, you can check that this is exactly how this works. In fact, right, if I write my cross product definition over here, so this is the determinant of this weird 3x3 matrix where the top row are these symbols for the vectors I, j, and k. If this is A1, A2, A3, this is B1, B2, B3. All right, so I'm taking that determinant. So if I did a scalar multiple times A, then each of these slots would be replaced with CA1, CA2, and CA3. And of course, when you do that determinant, this again is something that is immediate when you take 240. That if you multiply a single row in computing the determinant, that's the same thing as scaling the entire determinant. Okay, so and you could just compute this, that in every single term you're going to have an extra C factor that you can pull out. Okay, all right, so that's that. 3, and you can check this yourself. If I take a vector and I cross it with itself, I get the 0 vector. Now that should come as no surprise here, because we mentioned last time that if you had two vectors and you cross them and you get the 0 vector, that means those vectors are parallel or scalar multiples of each other. Conversely, that's also true. So this is an if and only if statement. Okay. And of course, the cross product behaves, there's a distributive property of the cross product. So if I have a vector A and I cross it with a sum of vectors B plus C, this is A cross B plus A cross C. Now, of course, note this is the distributive property. I can't swap the order here because the cross product's not commutative, so pay attention to the things that you can do. This is not something that's going to come up very frequently in this course, so you don't have to worry too much about that. Of course, 5 we saw last time, A and B are parallel if and only if, that's what this symbol means, A cross B is equal to the 0 vector. Okay. So that's a nice fact to have. And of course, number 3 is a special case of that because any vector is parallel to itself. Every vector is a scalar multiple of itself. The scalar in question is just 1, right? Okay. All right. And so this is a nice fact, but of course, as I said last time, you should never use this to check that two vectors are parallel. It's much easier to just look at the vectors and see whether or not they're scalar multiples of each other. Okay, so here's some algebraic facts about the cross product. Here's next my very important theorem about the cross product. Okay, so part 1. Okay. If A and B are vectors, then A cross B is orthogonal or perpendicular to both A and B. Okay, i.e., right, what does this mean? This means that A dotted with A cross B is 0, and B dotted with A cross B is 0. Right? Because of course the dot product is a nice way of telling when two vectors are perpendicular or are orthogonal. Okay, and so you can check on your own that this is always true. Okay, so pick any two vectors you like, A and B, compute their cross product, and then dot. Do these dot products, A dot A cross B, B dot A cross B, to see that they're 0. In fact, you can prove this just by doing it in general, right? So use the definition of the cross product and dot product to actually show this. Now, this is the first example of something called a triple product here, because yes, we're reusing vectors, but we're defining this dotting of a cross product of vectors. So you can imagine doing this for three generic vectors, A, B, and C. Okay, so here is the first part of this theorem. The second part of this theorem, this one isn't super duper important, but it's really, really nice to see the analog here with what we did with the dot product. Basically, the length of the vector A cross B is equal to the length of A times the length of B times sine of theta, where theta is the angle between A and B. So you see how there is this counterpart fact, right, to this fact, recall, from the dot product, right? So recall that when I dotted two vectors, this was the same thing as the product of the lengths of those vectors times cosine of the angle between them. Okay, and so for this other, very, very different product, the cross product, we get a very similar fact, right? So this is, you can think of this as being evidence that we're definitely on the right track here in terms of defining these products, because clearly these are nice, and they even have this kind of almost duality thing going on here. Okay. All right. So a couple of things that I wanted to mention here. So first, let's do a quick example. So let A be the vector 4i minus j plus 3k, and let B be the vector 2i plus 3j minus k. So find a vector perpendicular to A and B. Okay, so you weren't asked directly for the cross product here, but the cross product is what you're going to do because we know from this last theorem. First part tells us that the cross product of two vectors is perpendicular to both of them. And so to do this, let's compute A cross B. So I do this determinant once more. So A is 4 minus 1, 3, and B is 2, 3 minus 1. So computing this, what is the term multiplying the I? So I'm going to quickly compute these determinants here. Maybe I'll write them out like this. So I have something times the I term. What is that? It's the determinant of this matrix minus 1, 3, 3, minus 1, right? So it looks like that. Okay. So this is minus 1 times minus 1 is 1. So this is 1 minus 3 times 3 is 9. So this is 1 minus 9i minus something times j. So there we go. Right. So this is 4 times minus 1, so it's minus 4, minus 3 times 2, so minus 6j, plus something times k, and there we go. All right, so this is 4 times 3, which is 12, minus 2, okay, times k. So this is minus 8i. This is minus 10, so this minus makes it plus, so this is minus 8i plus 10j plus 12 minus 2, so that's plus 14k. Okay, so there it is. All right, and you can actually check by dotting this with either A or B, so you can do that. So check that A dot A cross B is 0, and B dotted with A cross B is 0. And you'll see that, in fact, both of those are true. And so this is perpendicular to both A and B. This is going to be our primary thing that we use. This is our main use of the cross product, not just our main use. This is basically our only use of the cross product. Almost every time we use the cross product, it is exactly for this purpose. Okay, so a couple of geometric facts that I wanted to state before moving on. So more geometric facts about the cross ratio. Or maybe I should say A cross B, because that makes it look like I'm just saying more geometric facts about X. So if I have two vectors, say A and B, okay, if I have an angle between A and B here, theta, okay, well, here's a question, right? What if I wanted to, these are not even straight, so I don't know why I'm breaking out the ruler now. What if I wanted to find the area of the parallelogram determined by A and B? Okay, what is the parallelogram determined by A and B? So that doesn't have an E. Parallelogram determined by A and B. Now, in order for this parallelogram to actually be a parallelogram, A and B would not only need to not be the zero vector, A and B would also need to be like this, right? That is, not be scalar multiples of each other. If they're scalar multiples of each other, then they don't determine a parallelogram, they determine a line. And that's a notion of what's called two vectors being linearly dependent, which is a degenerate case. So we want, of course, what we come up with will take care of that. So you don't have to worry about that in this course. Okay, again, that's a thing for 240. This is general position for two vectors A and B. What's the parallelogram determined by them? Well, it's just the obvious thing here, right? I copy these vectors in this way. Of course, this looks really mega terrible because my vectors didn't start out straight. Okay, but this is the parallelogram determined by A and B. You'll just have to use your imagination here. Okay, so what if I wanted to compute the area of this parallelogram? How do I compute the area of a parallelogram? Well, remember, the area of a parallelogram is computed in the exact same way the area of a rectangle is computed, right? Which is length times height, right? Where here is the length. Well, what's that length? If that's vector A, that length is the length of A. And what's the height here? Remember, it's not the slant height, it's the actual height. What is that height? Well, if this is B, and this vector, of course, has length B, and what is that? Well, just by basic trig, right? This is a right triangle. And so what is this side? This is the length of B times sine theta. This is just basic trig, right? So then length times height would be the length of A times the length of B times sine theta. But what is this? Well, we saw previously, right? It's the length of A cross B. Okay, so it's this, i.e. the area of the parallelogram determined, why do I keep putting an E here? Parallelogram determined by A and B is the length of A cross B. Well, that's pretty neat. In fact, there's a more general thing at play here, which is that determinants are tied in with this. So this is because of properties of the determinants, basically. Yeah, so I was asked in chat, is it just A dot B, not the magnitude of A dot B? It's just A dot B. The reason it's just A dot B is consider, right, the fact that the dot product can be negative. Right? You can dot two vectors and it be negative. That's perfectly fine because cosine of theta, right, between 0 and pi, that can be negative. Okay. So anyway, so yes, it's just there's no absolute value sign slapped on A dot B in that formula. Okay, so the only reason that I mention this really, it's not that you're going to be doing this too much. The only reason I mention this is because of its tie-in with what we're going to talk about next. It's going to be the last thing I mention about cross products, which is the following. So it is how this ties in to area and volume in the following way. So consider the parallelepiped. So our previous example was in the plane. Our vectors A and B were in the plane, right? We talked about the parallelogram determined by them. So consider a three-dimensional analog of a parallelogram, the parallelepiped determined by the vectors. We'll say U, V, and W. What is the parallelepiped determined by three vectors? Okay, this is going to be a terrible picture, but this is the idea. Again, there's some assumptions here about these things being in general position. It doesn't matter because in the bad case, in the degenerate cases, our formula will handle it just fine. So here's vector V, and here's W. Maybe I should have made this slightly bigger. Actually, yeah. Okay, my bad picture was going to be even worse. So here's U, here's V, and here's W. Now, of course, I've not done a good job of like giving you some perspective here of what these vectors actually look like or where they're sitting. Here's the idea. In three-dimensional space, parallelepiped determined by three vectors would be this sort of thing. So maybe I should dot that, yeah. Oh, this is really bad. Here we go. Okay. An attempt was made, all right? So anyway, if you look at parallelepiped, you'll get a lot better pictures than this. So the parallelepiped determined by three vectors U, V, and W looks like this. How do I compute the volume of this? So here's a fact. The volume of this parallelepiped is the absolute value of U dotted with V cross W. Why? Because this can be interpreted as a determinant, and determinants behave this way with respect to area and volume. Okay. Parallelepiped, yes, that's the word. Yeah. Okay. So you could think about this for a second. You could say, why do I need an absolute value sign? Well, without it, a dot product of two vectors can be positive, negative, it can be zero, right? We wouldn't want a volume measurement to be negative. Right? We're not talking about any kind of net volume thing. We're talking about the absolute, volume of some geometric object. So we want that to be positive. You might also say, wait, I've said this is the volume of the parallelepiped determined by U, V, and W, but then you have these in this order, U, V, W. Is that the same thing as, the absolute value of V dotted with U cross W? Or the absolute value of W dotted with, say, V cross U, right? Are these all the same? Sorry, I'm off page a little bit. They are. All these quantities are actually the same. And so where does this show up? This shows up as basically just a way to ask you a question about doing these computations, right, without just being very boring. So, if I wanted to be very boring, I would just say, compute dot product of these two vectors, right? Or compute cross product of these two vectors. So a way to give you a problem that has you doing what I want you to do without me just saying compute dot product or compute this. I can say compute the volume of the parallelepiped determined by these three vectors. Okay, and this is how you do it. Okay, so you'd cross two of them, any two you want, and dot them with the third. Okay, and it doesn't matter what order you do that in because of the absolute value sign. All right. So, if you have any lingering questions about the cross product, you can put them in the chat. But otherwise, I'm going to move on to our discussion of lines. Okay, so here is where we actually are going to start applying these. We've taken a good bit of time to set up this background work, so now I want to use it. So lines in space. Okay, so what does the picture look like? Oh, I'm off camera again. What does the picture look like here? So I have a line L cutting through space like this. Okay, so you're familiar with lines in the plane, of course. The thing that defines a line, right? This is straight from Euclid's postulates, is that 2 points determine a line. Right? Now, of course, in the plane you had other pieces of info that were equivalent to it, like if you had a point and the slope of the line, that was good enough, right? But ultimately, 2 points determine a line. That was the fundamental property, and so we want to try to do the same thing, right? In a plane, if I had told you to write the equation of a line, you have absolutely no problem doing that. So I want to do the same thing for a line in space. Geometrically, a line in space is really the same kind of thing. And even what was true in the plane is true here, that a line in space is determined by 2 points. Okay, so ultimately, whatever we come up with here has to agree with this notion that if I have 2 points on the line, I need to be able to write out the equation for it, period. So that's something that we're going to work with. Now, that's not what we're going to start with. Okay, we're going to start with something slightly different that we're going to see as equivalent to 2 points determining a line. So what does this picture look like? Okay, so here's the origin. Here's my x-axis. Here's my y-axis. Here's my z-axis. Of course, I'm always going to use that orientation. What is the idea? Well, the idea is, suppose I have a point here. This is some initial point that I know, right? So I know this point. I'm given this point. Okay, so this point has coordinates x naught, y naught, z naught. Okay. Now, of course, there's a vector that this point determines, pointing from the origin to that point. We'll call this vector r naught, or r sub 0. Okay, and of course, if that point, right, has coordinates x naught, y naught, z naught, then we know what the components of r naught are. So if I write r naught in this ijk notation, this is just x naught I plus y naught j plus z naught k, right? Okay. All right. Now the idea would be to come up with an equation or a set of equations that explains the position of a general point on the line. So say a general point on the line is this point P, which has the coordinates just x, y, and z. So the idea is that I want to come up with equations that give to me, the set of coordinates x, y, z, satisfying blah set of equations that determines or describes this line in space. And of course, there's another vector pointing to that point that I'll call r. And of course, this r that we're seeking has components x, I plus y, j plus z, k. All right. Okay. So then what are the 2 pieces of info to determine this line? I want to give the 2 pieces of info as an initial point P naught and a vector L that is parallel to the line. So I have a vector L that is parallel to my line little l, and this together with an initial point is going to determine my line. So what I need. Okay, 2 pieces of info. A point P naught on my line L, and secondly, a vector big L parallel to my line L. Okay, this is what I need. Now you might say, where did our discussion of a line being determined by 2 points go, we'll see that this is equivalent to that. Okay, so we can recover that description of a line from this, but this is how we're going to start because we'll see that it's easy here. So what is the idea? Okay, since we know that this vector L is parallel to my line little l, what that means is that if I consider the vector that has initial point P naught and terminal point P, right? What does that vector look like? That's just this vector here, right? So that is a vector that lies on L. Maybe I'll label that vector. It's the vector P naught P, right? So that lies on my line L. Since big L is parallel to it, what do I know? I know that this has to be a scalar multiple of that vector big L. So it is TL, where T is some scalar. Remember, a scalar is a real number. Now, the reason I'm stressing that here is the following. How am I thinking about this? The idea here is that I'm thinking of an initial vector R naught, okay, and as T progresses, this R naught is tracing out this line L. Okay, and so at some point T in the future, R naught passes through this vector, this generic vector R, and then it keeps going. You might say, wait a minute, that's only half the line. How does it trace out the rest? Well, that would be for the negative T value, since T is just some scalar, some real number. So the negative values would go in this direction. So considering all possible T values, I have this vector R naught, and it's tracing out this line L in space. It's nice to visualize it in this way because, as we'll see in chapter 12, we're going to talk about things that are more general than lines. We're going to talk about curves in space. And this way that we're formulating it is going to apply to curves easily, and it's going to allow you to visualize how this works for curves as well. And so what do I get from this? So using all of this notation here, note that P naught P is actually just R minus R naught. All right, that's just the definition of this. And so what do I get? I get this vector equation, R is equal to R naught plus TL. Oh, I'm a little bit off the page. There we go. Oh, so R naught, I'm saying R naught for 0. All right, this is like a... Exactly. This is R sub 0. R naught. Not. That's what's being said. Yeah. Anyway, so yeah, I'm probably gonna do that throughout the course. So anyway, oh yeah, my R's do kind of look like V's. The V's don't have, when I write V's, they don't have this little overhang though. Yeah, I know my R's look like V's. I'm sorry. But anyway, yeah, that's how it's gonna be. My V's are more they're more open than this, and they don't have the little curl on the tip. Okay. So this is the vector equation for a line. Now there's a more useful form of this, and to see that, I'm going to use this same notation, but I am going to say, let's suppose that this parallel vector, big L, we know what this, we're given this, right? This is what I need. So I need a point, P naught, and I need a vector L that's parallel to my line. So here's my vector L, right? And I'll say that this is A, B, C in IJK notation. So it's AI plus BJ plus CK. Okay. So then how can I use this to put my equation for a line in a slightly better form? So then just literally, maybe I'll keep this on the page because I'm just going to use the exact same notation. So what I have here is the following. So I'm going to write this in this component form where r is x, y, z, and that is equal to r naught, which was x naught, y naught, z naught, plus t times L, which I labeled A, B, C. Okay. And so on the right-hand side, this is equal to, this is just adding vectors. Of course, t is a scalar times vector, so I can just multiply each of these components by t. So this would be ta, tb, and tc. Adding those, I would get x naught plus at, y naught plus bt, and z naught plus ct. Okay, and so I have the statement, I have a vector, xyz, is equal to another vector, and there's the three components, x naught plus at, y naught plus bt, and z naught plus ct. Well, if two vectors are equal, I didn't really talk about this before, but if two vectors are equal, what does that mean? It means all of their corresponding components are equal, right? So if you match them up by components, all of the components have to agree. And so what I get out of this, if I break that down, is that x must be equal to x naught plus at, y must be equal to y naught plus bt, and z must be equal to z naught plus ct. These are the three equations that determine a line in space. These are called the parametric equations. So these are the parametric equations of a line L in space. Okay, so there will be two main ways of writing equations for a line in space. This is one of them. It's called the parametric equations for a line. There will be another form called the symmetric equations for a line that we'll see here in a second. Okay, so let's just do an example, right? The simplest possible thing, where you literally have to do almost no work, is when you're given exactly what you need in this form. What does this say you need? You need a point P naught on the line and a vector L that is parallel to the line. If you have that, then you can just immediately write out the parametric equation. So let's do that. I'll just use example 1 from 11.5 in the textbook. So this is find the parametric equations of the line containing the point minus 1, 3, 0 and parallel to the vector 2i minus 3j, minus k. Okay, if I'm just following this example exactly. Okay, well, again, here, where did x naught, y naught, z naught come from? Those are the components of my point that was on the line. Where did a, b, and c come from? Those were the components of the vector that's parallel to the line. And so what are the parametric equations of the line containing the point minus 1, 3, 0 and parallel to this vector? Well, they're just x is minus 1 plus 2t, y is 3 minus 3t, and z is 0. You don't have to write this. I'm just doing it so that you see. Minus 1 times t. Right? And t is just some real number, just some scalar. Okay, here are my parametric equations for that line. Okay, now how are you supposed to view this geometrically? Okay, all right. So the idea here is that this describes every single point x, y, z, okay, that can possibly lie on this line being described here. And this is a completely unique way of describing the line. Now, this might be a little bit confusing. The question is this the only set of equations I can write? Like literally, is there any other set of equations that looks even remotely different here differently here that I can write that describes the exact same line? The answer is yes. Okay, so this description, these equations are not unique in the sense that I can change them slightly, right? That should be no surprise to you, right? So let's go back to like algebra 1 here for a second. If I have maybe a line that looks like this. Oh, I'm a little bit off the page. Say I have a line that looks like this. What is this line? This is like, I don't know, y is 2x plus 1. Okay, there's that line. And of course, written in another way, I could write this as minus 2x plus y is equal to 1, right? That's a way of writing this linear equation. But this isn't the only way to write this equation, right? What about this? Right? And you might argue and say, well, that's just a stupid way of writing it, right? But of course, like there's nothing necessarily that's nicer about this form over this form. In fact, maybe I don't want this 2 here. Maybe I want to divide by 2 so that I have 1/2 y here and 1/2 on the right hand side. The idea is that there are these dumb things you can do in this way. Similarly, there are things you can do in our example here to make this look slightly different. Well, what's one example, right? I didn't have to give you this point. A line contains infinitely many points, so I could have given you some other point on it, and in that case, these would have been different, right? Instead of having -1, 3, and 0 here, I could have given you another line or another point on this line. In fact, someone tell me another point on this line. Well, I'll make it easy for you. If I set t equal to 0, what point do I get? My initial point. What if t is equal to 1? All right, so if t is equal to 1, what point do I get? X is equal to -1 plus 2, so that's 1. Y is equal to 3 minus 3, so that's 0. And z is equal to -1. So here is another point on that same line, and I could have used this point instead. So if I wrote my equations for my line as 1, so let's rewrite. Say x is 1 plus 2t, y is 0 minus 3t, and z is -1 minus t, and t is just some real number. This is the same as this. So these two equations describe the exact same line. Now you might say, how could that be? Well, all you've done is you've just initialized the initial point differently, right? So here, the initial point is clearly -130. When t is equal to 0, you get -130. Here, the initial point is 1, 0, -1. So when t is equal to 0, you get 1, 0, -1, which is the point corresponding to t equals 1 for this description of the line. So it's not that the equations are unique. They're not, right? Here's two examples that show that they're not. The equations themselves aren't unique, but the line they describe is the same line. Okay, they're just two different ways of describing the exact same line. Okay, so that's one thing that can come up here, right? Okay, so continuing on, the main thing we want to say here is what's the next example? I want to make sure that this meshes with what we know about lines, right? So for instance, how do I use this to find the parametric equations? So find the parametric equations of a line, or of the line, containing the point, let's say 4, -6, 5, and 2, -3, 0. All right. So remember, what do I need? Right? I need a point on the line, Well, I have 2, so I'm good there. I can use either of these. What else do I need? I need a vector parallel to my line L. So question, where do I get my parallel vector L? Well, if I call this point P0 and I call this point P1, what is the vector that's parallel to my line L? It's just the vector that has initial point P0 and terminal point P1. Now you might say, could you have used the vector going the opposite direction? Absolutely, right? That's also parallel. Okay. And so we could do this in the exact same way. Now, rather than finishing this example, I think since I only have a few minutes left, it's better. It is better than that I mention one other type of equation just so that your TAs can go over it tomorrow in discussion, which is our one other way of writing equation of a line, which is symmetric equation. What are the symmetric equations for a line? I'm going to start out, again, I'm going to rewrite the general parametric equations for a line. Okay. The idea here is I want to solve for t in each of these. So I'm going to assume, firstly, that A, B, and C are all non-zero. This isn't always the case, right? Sometimes it's not the case. Sometimes the info that you're given, one of these or more is 0. We'll see what happens in that case. But for now, let's assume that none of them are 0. I want to solve each of these equations for t. So I'm just going to do that, right? So I would subtract x0 from x, and then I'd divide by a. Right? So the first one, I'd get x minus x0 over a, and that's equal to t. In the second one, I would get y minus y0 over b, and that's equal to t. Now you see why I wanted a, b, and c to not be 0, because I'm dividing by them. Here, this would be z minus z0 over c. That's equal to t. Okay, but now, all these things are equal to t. So they're equal to each other. So what this means altogether is that x minus x0 over a is equal to y minus y0 over b is equal to z minus z0 over c. I have eliminated this other quantity t entirely by setting them equal to each other because all of them are equal to t. These are called the symmetric equations. So these are the symmetric equations of the line containing the point x0, y0, z0 and parallel to the vector L, which is ai plus bj plus ck. So these are the symmetric equations. So when you are given a line, or when you're given a description of a line on an exam or in homework, it will typically be in the form of either the parametric equations for that line or the symmetric equations for that line. Now, before I do some examples, because you're going to do examples of these tomorrow in discussion, and so before I do more examples, I'll do a couple of examples on Friday before we move on to planes. But I wanted to mention, what happens when you don't have this? What happens when you're in one of these tricky cases where one of these is 0 or maybe even two of them is 0? Well, suppose that a is equal to 0. All right, so one of them is equal to 0. Might as well suppose that it's a. You can do something similar if one of the others is 0. So in this case, let's write what the parametric equations would be. Let me just remind you, that's what the parametric equations look like. But suppose that a is 0. Well, then what you get is that x is equal to x0, right? So a is 0, so that term goes away. And we're left with x is equal to x0, y is equal to y0 plus bt, and z is equal to z0 plus ct. So x is actually constant. The x slot is constant. It's just always equal to x naught. Okay. And so how would you write the symmetric equations? Well, you can still solve for t for these two equations. And so what would the symmetric equations be? Simple. It's x is equal to x naught. And then also y minus y naught over b is equal to z minus z naught over c. So there would be your symmetric equations in that case. All right. Real quickly, to just cover all of our bases here, because someone is obviously thinking the exact same thing. What happens if 2 are 0, right? So suppose that both a is equal to 0 and b is equal to 0. Again, it doesn't matter which 2 it is, the similar thing happens. All right, well, in this case, what do my parametric equations look like? I would get x is equal to x naught, y is equal to y naught, and z is equal to z naught plus ct. Right? How would I describe that in symmetric equations? Well, as it turns out, all I need to do is say x is equal to x naught, y is equal to y naught. I don't have to say anything about z. Why? In this particular example, what would a line like this look like? Well, if here's my xy plane, right, and in space, so my z-axis is coming straight up out of the paper, then what is the line that is, that contains a point x naught, y naught, z naught, and is such that it's parallel to a vector that's first two components are 0? Well, a vector like that looks like this. It's just vertical. And so if this is the point x naught, y naught, 0, this is a point on that line, and the line in question is just the vertical line through that point. That's why I don't have to say anything about z, because it's just all of the points, right? All of the scalar multiples of vectors that are vertical through that point x naught, y naught, 0. Okay. Exactly, yeah. This would be a vertical line in that case, passing through that point in the xy plane. Okay. All right. So that's that. That's how to do it. There's only one other thing that I want to talk about as far as lines in space, but I'll do a couple of examples just to give you some practice with this. But this is primarily what you're going to be practicing with tomorrow in discussion with your TAs. Okay. Yeah, Daniel. So the right-hand rule is when you're doing a cross product vectors a and b. So here's a, here's b. Okay. To determine the direction of a cross b, you take your right hand, you take your fingers of the right hand, and if you're doing a cross b, you would curl those fingers from a to b, like this. When you curl those fingers like this is telling you the direction of your fist, basically. There's only two directions. It's either up or down. Right? And so since it's a cross b, here a cross b would point up out of the paper. If we were doing b cross a, because I would have to turn my hand like this to curl my fingers, my thumb is now pointing directly into the page, so it would be into the page. It would be the opposite direction. Okay. All right. So homework will be posted later tonight. Don't worry too much about the homework. You'll have plenty of time to do it. It will contain most of the sections in Chapter 11. I may also, just because we're going to cover it next, I may also assign point or problems from the last section of Chapter 11, which is 11.6. Anyway, so I will see you all on Friday, where we will finish up Chapter 11 and start on Chapter 12 on Monday. So yeah, anyway, I'll see you then. You have discussion tomorrow where you will do a bunch of examples of lines in space, cross products, and basically everything everything contained in Chapter 11 except planes. So that's the idea. Anyway, so yeah, I will see you all Friday. Discussion tomorrow. Homework tonight. I will post it. You'll have, days to do it.